Okay, my name is Alan Davis, and I am presenting the experiment we didn't do the AC charging cycle. So, an overview, we're going to go with a recap of basically what the experiment was. We'll go through our expected results, then how we calculate out what we're actually looking for, the coefficient of performance, then what we actually got, and then a discussion and conclusions after that. So, to recap, we were running a refrigeration cycle, or supposed to. So, you would have essentially running through what is the opposite of the heat cycle we did before. And the goal is to use Freon as our working fluid to take heat out of it and discharge it with a work input coming through the So the expected results for an ideal cycle has it work coming in through the compressor, it's cooled down, goes through the throttle, and then the heat is taken in to the working fluid and discharged. So this is our expected temperature and entropy charts, and our pressure and enthalpy for the cycle. So the coefficient of performance is a measure of the efficiency of the cycle. That's what we're actually looking for here. So it can be affected by the heat at the low cycle, which is taking it out of the air in the case of this, over the work put in to the compressor, which is the energy we had to take in for the system to work. And there's when we're actually using is here, but an ideal cycle would get all of the energy out of it, and it would just be based off of the temperature and the temperature differential between the high and low reservoirs, which also ideally would be the same temperature for the high reservoir and low reservoir, but in reality that is not always the case. So calculating the amount, since the mass flow rate for the system at any point is constant, then we can take that out and we can do this based off of the enthalpies. And once again, this is based off of the Carnot cycle, which is important because it gives you a baseline of how efficient in theory the system could get, even though we're never actually going to get there. So, using one of the other lab's experiments, seeing as we didn't have one, also using a range that we were supposed to have from 14 to 17 pounds, but none of the groups appeared to get that either. We have our state 1, and from here it's compressed and heated up and turned into a vapor state, at which point it's then condensed down and the temperature is reduced, but you lower the pressure, and then from there you lower the pressure with the release, and you go back to your low temperature. And as we can see, while the temperature is supposed to be the same at the high and low states, or constantly on them, at the low state, it actually, you lose it because you go from, say, 41 degrees here to 73 here. But when it goes across the supposedly isothermal boundaries, it actually does lose heat in the process. So, calculating out based off the enthalpies for the amount of Freon, we see that the Carnot coefficient of performance is obviously much higher than we can attain from our temperature gradients. And our actual coefficient of performance does change with the amount of Freon we use, and it does improve. So, ideally we would have liked to have a full range from 14 to 17 to see if there's an amount that your coefficient is the most efficient. But as it is, it was for the most part increasing. It didn't have a bump up by going there, but that was adding 2 ounces of Freon instead of a pound of it. But as you can see, the coefficient performance compared to how much Freon we used also increased. And we have here a table that shows basically how much we can expect it to increase. Obviously, it won't do that as it goes all the way up, but we don't have an experiment that shows it at the higher milligrams of this. So it makes for a pretty clear indicator of how increasing Freon increases the efficiency. We also calculated the mass flow rate based off the humidity leaving and the velocity. Since the mass flow rate was constant, you only needed to know one location. And using the thermodynamic tables and the humidity, you could calculate it out using your rho times velocity times cross-sectional area, which I pulled from just one of the posted pictures online, since we did not take the measurements or run them on lab. So, discussion, the system was much less efficient than a Carnot equivalent. The coefficient of performance increased with the amount of Freon, but we had a limited sample size for the range, so it's expected that as you lower it and increase it, that it has to taper off at some point. So, then we didn't actually do this experiment, so the data was just taken from the lab and the measurements were made from that, and it's a fairly inefficient site. Any questions? And references.